Welcome again to the study of the molecular physics. Dear students, we are going to have in this class rotational spectra or microwave spectroscopy. The microwave spectroscopy shows its output as rotational spectra. When electromagnetic radiation in the microwave region falls on the matter, it gives out a rotational motion. The molecule set into rotational motion. When the molecule set into a rotational motion, it absorbs energy which is similar frequency of its matter and the electromagnetic spectrum, absorbs energy, goes from ground state to the excited state, and this absorption is recorded in the computer as spectra. In this study, we will go deeper into some of the molecules based on its rotational motion. We will have following things in this slide. We will have introduction and some explanation about the classification of the molecules and discussion on the applications. Spectroscopy in the microwave region is concerned with the study of rotating molecules. So, the molecules, those have permanent dipole moment. Be careful in listening to the word molecules having permanent dipole moment can absorb or emit electromagnetic radiation. So, it clearly excludes those molecules which do not possess the permanent dipole moment, cannot absorb or emit electromagnetic radiation. In the rotation of HCl, which is said to be the linear molecule, the fluctuations seem to be exactly similar to the fluctuation of electric field of radiation. Thus, interaction can occur, energy be absorbed or emitted, and the rotation gives rise to a spectrum. So, spectroscopy in the microwave region is concerned with the rotating of molecules simply. We know that the spectroscopy in the microwave region speaks of rotations. The rotation of a three-dimensional body is quite complex, and it is resolved into three perpendicular axes. That is center of gravity, the principal axis. Thus, a body has three principal moments of inertia, one about each axis. They are designed as IA, IB, IC. Let us go to the classification now. We can group the molecules according to their values of moments of inertia. How they give out the moments of inertia, the values of moments of inertia, basing on its shape. We will discuss now the rotational spectra arising from each group. Each group gives us the rotational spectra. Basing on the rotational spectra, we will discuss now. The first one is linear molecules. The molecule which are connected in straight line, as the word defines, it is the atoms connected in a linear form. Example, HCl and OCS. The three direction may be taken as the first one about the bond axis. The second one could be end over end rotation in the plane of the paper, and third one is end over end rotation at right angles to the plane of paper. So here in this linear molecule, it is self-evident that B and C are same, and A, that is the rotation along the bond axis, is considered to be very, very small. So as an approximation, we can say IA is equals to 0 and IB is equal to IC. Then we come to the second type of molecule, that is symmetric top molecule. Consider a molecule such as methyl fluoride. The figure is shown at the bottom. The three atoms bonded tetrahedrally to the carbon atom. Here we cannot consider bond axis CF, that is axis along the main axis. The rotation is possible because the three hydrogen atoms rotates along keeping this axis as principal axis. So we cannot simply consider the CF going to be 0. And such a way about the axis is imagined as top. Thus the name comes. Therefore, the symmetric top will have IB is equal to IC, that is possible, and IC is not equal to IA, therefore IA is not equal to 0. This type of molecule has got two subdivisions, that is prolate and oblate. The methyl fluoride, just we have seen in the previous slide, falls on the type of prolate symmetric top molecule. Here the values of moment of inertia will be IB is equal to IC, but IC is very much greater than IA, or IB and IC are very much greater than IA. In the case of the second type, oblate, here the values of moments of inertia are different. IA is equal to 2IC is equal to 2IB. Then we'll go to the next, that is the next type of classification of molecule is spherical top molecules. When molecule has all the three moments of inertia identical, it is called spherical top. For example, tetrahedral molecule methane. Here all the moments of inertia are identical, thereby it cannot have permanent dipole moment. So simply rotation alone cannot produce dipole moment. So in this type of molecules, we cannot get the rotational spectrum. Then comes the fourth type of molecule, that is asymmetric top molecule. Asymmetric. It is not symmetric. That's the meaning. These type of molecules to which majority of the substance belong. In this type of molecules, all the three moments of inertia are different. We can take two examples here, water and vinyl chloride. You have just seen here, the moments of inertia are all the three are different. IA is not equal to IB and IB is not equal to IC. So basing on these types of molecules, we can in the next slide, in the next talk, we can discuss about how the two diatomic molecule, how the diatomic molecule, atoms connected by a bond, two atoms connected by a bond, gives us the rotational spectra. In the next slide, we will discuss. Thank you. And this is a few examples here about different types of molecules: linear, symmetric top, spherical top, and asymmetric top molecules. We will have a small discussion here basing on the discussion that we had in the previous slides. Which type of molecule does not show rotational spectrum and why? All the homonuclear molecules like N2, O2, all these things, they do not possess permanent dipole moment. Therefore, there is no dipole change. As a result, these types of molecules will not produce rotational spectra. The moments of inertia is very, very small about the bond axis. Therefore, no change in dipole, no change in the dipole moment, and thereby no spectrum. But we will study in the next few classes, in the next unit, when we study the Raman spectra, how these homonuclear molecules can also be active, can also give us the spectrum. That we will study in the next classes.